Okay, welcome to video 3 for the basic concepts of electricity unit nodes. Now in this one we're going to start by talking about current. Current is the flow. You know, if voltage is all about potential energy, current would be all about kinetic energy. And that's not a perfect analogy, but it's a close analogy. Now, in terms of units, the voltage, or the volt, is a joule per coulomb. That's the unit for volt. Current, which we represent with an I, believe it or not, is an amp, or an ampere. You may be wondering, why do we use an I for current? Well, it comes from the word intensity. When scientists were first studying electricity, the way they thought of current was how intense the electricity was. So that's why we use an I for a current. Now, looking at the water tower analogy from earlier, the current would be determined by the speed of the water in the pipes. Electrons behave in a similar fashion. Now, if we think about it, we can speed up that water in a couple ways, by trying to force more water through the pipes, or by making the pipes, the diameter of the pipe bigger. That would speed up the water, so that'd make for a larger current. So that's something to keep in mind. Now, again, this means that there cannot be any breaks in the path. If there's a break, the electrons will stop flowing. Now, current, the way we define it, we define current as the path a positive charge would take. So, So if we had a positive charge, it would be repelled by the positive end of the battery, and it would be attracted to the negative end of the battery. So current always leaves the positive terminal and enters the negative terminal. And if you think about that, that means it's opposite the direction that an electron would take. And that seems really counterintuitive until you remember that when Benjamin Franklin was discussing his theory on that fluid, he defined it as going from positive to negative. So this is actually because of Benjamin Franklin. The reason why we take this convention. It's not perfect, but it's what we have to work with. All right. Now, the circuit on that previous page that we just looked at, it would be very dangerous to build that circuit. The magnitude of the electrical current may be very, very large in such a short circuit, and the release of that energy would be very dramatic. What we want to do is we want to regulate the flow of electrons by slowing them down. And to do this, we need to add some means to the circuit to resist the flow of electrons. One popular way is to use something called a light bulb. This light bulb would slow down the speed of the electrons so that they don't spin, they don't go around as fast. So looking at this diagram right here, the current would start here, it would flow down, the current then would go through the light bulb, or the load, come around here, and then notice when the switch is open, the electricity could not flow through. But if the switch were closed, it could then return to the battery. Now, what this is then is the light bulb acts as something called a resistor. A resistor slows down the electricity, resists the flow of electricity. We can use a light bulb symbol. I typically use this, or we can use this symbol right here for a resistor. The unit is the ohm, and we use the capital omega symbol for its for the symbol of the ohm. We'll talk more about ohms later. Now, something to notice that when the switch is open, no electrons can jump across because air is such a good insulator. The current will not flow. Also notice the term load. Before, we use load to express the external torque we place on a motor. Here, load refers to something that resists the flow of electrons. So if you think about it, it's kind of a similar thing. It resists motion. All right, well, that concludes the video notes for this entire unit.